One hallmark of many engineering disciplines is looking at information, at systems in the frequency domain, not just in the time domain. If you don't know what that means, this video is probably going to be a little crazy for you. And so, but most engineering students know what I'm talking about when I'm talking about Fourier transform, Fourier series, and the frequency domain. So that's what this lesson is going to be about. The overall, when I'm trying to do frequency analysis, I often use Octave or MATLAB. There are a lot of useful tools in Octave and MATLAB in the frequency domain, so it's really easy to see what I'm doing there. So it's a great tool for doing frequency analysis. All right, first step, in the whole video, I'm going to generate a signal that's just the sum of a few sine waves, cosine waves. And then I'm going to take the Fourier transform, the fast Fourier transform, FFT, and convert it to the frequency domain and see if I can see it in the frequency domain and see if it makes sense. Good? For the students in my class, I'm going to give you a signal, an electrocardiogram signal, and you're going to have to take the Fourier transform of that and do the exact same things that I've done with this manufactured signal with the actual ECG signal. Good? All right. Okay, so first thing, I'm going to just start a new project. And so I go into my Octave folder, I make a new folder. I'm going to call it DrO underscore FFT1. There's a little note about naming things that I'm going to talk about is there's already an FFT function in MATLAB and Octave, and there might even be FFT with numbers behind it stuff. And so as we get more and more advanced in MATLAB script writing and programming, you might run into the problem where you're going to try to name a script something that might already exist. It's a deal. So don't do that. The way I avoid that is I usually use my initials. I'm not going to use my initials here. I'm just using DrO because that's the name of the video series and all that. So I say DrO underscore something, or DrO, then the name of something that I'm interested in. Right? So that's my strategy. You should just use your initials. Don't use DrO, you don't have to. Just use your initials, then underscore FFT1 if you want. Then I go into Octave, I get into the right folder, and then I'm going to say edit DrO FFT1.m. No spaces, no nothing. I tried it a different way and it balked on me. So I've been having situations where the name of the script that I'm using is weird and Octave doesn't like it. So you might have to if you're having the same kind of problems, experiment with uppercase, lowercase letters, underscores, no underscores, that kind of thing to try and get one that actually runs. All right, but so mine's going to be called DrO FFT1. I'm going to manufacture a signal. It's just going to be the sum of 3 cosine waves with different phases. And the frequencies of those are going to be 20 hertz, 30 hertz, and 40 hertz, right? And they're going to have different magnitudes of each of them. I'm going to set my sampling frequency. I'm going to make a digital version of this, a digital signal, right? And so my sampling frequency is going to be 1,000 hertz. I'm setting that to be 1,000 hertz. And then I'm using 1,000 points. I just picked that arbitrarily. Good, everybody see all that? So that's the setup here. Then I'm going to set my time axis. My time axis is delta t. Delta t is 1 over fs, and then it's going to go from 0 by delta t to n minus 1 times delta t. So that's going to be the time axis there. Then I'm going to calculate my signal x, right? X is just going to be equal to the sum of 3 cosines, and so it's going to be 2 pi times f1. So that's omega 1, and then there's a phase angle there, and 2 pi f2 times t inside the cosine wave. And so you see the 3 angles. You see the 3 magnitudes there, 3, 1, and 2. So there's 3 phases, 3 magnitudes, and we ought to be able to see that in the Fourier transform. I plot it, I take a look at it. It's this weird signal. I don't know what I mean. It has no meaning whatsoever. It's just a weird sum of 3 sine waves. Good? The next step is just to take the Fourier transform of it. FFT, the fast Fourier transform, is one of the most used algorithms in the world. Lots and lots of big data mining operations and data analysis operations use the FFT all the time. It's super common. Most algorithms use, I'm not dead sure about this, but I think it's all FFTW, fastest Fourier transform in the West. Surprisingly, it was done in Massachusetts at MIT with a bunch of MIT guys, but West meaning the west of the world, not the west of the United States. And so fftw.org has the algorithm and in all sorts of languages, and so you can look all that up. MATLAB, I'm pretty sure MATLAB uses FFTW too. It's a really good algorithm. So you don't need to know that algorithm. You just pretend you don't know it and just use the FFT. And so I'm going to say capital X is equal to the FFT of lowercase x. This is a convention for a long, long time in MATLAB and Octave, is that frequency domain variables are caps and time domain variables are lowercase. It's just, and by the way, when you take signals and systems classes and control systems classes, that's a common convention as well. And so it's not like they made it up themselves, they just used an existing convention. And so I'm doing the same thing. So capital X, and again, MATLAB and Octave are case sensitive. And so, of course, capital X is not the same thing as lowercase x here. When I run the script, I get the answer and I look at what capital X is, and it's all complex numbers, and that makes sense, right? Is that you're going to get real and imaginary components for everything because there's going to be a magnitude and a phase everywhere of your FFT of a time domain signal, right? So the fact that it's a complex number, that's good. I want to double check, so I'm just going to look at the magnitude of X. I'm just going to look at the values of X. I'm going to say between like 29 and 34. I'm going to try to hit the 30th harmonic there, right, to take a look at it. And so that's what I'm doing there on the screen. You can see the 31st element of capital X, right? The others are 0, 10 to the minus 13, 10 to the minus 12, whatever. They're all really, really small, but that one's not small. It's 355 minus J 355, or I 355 if you're a mathematician, not an electrical engineer. Right, that's a lot. Those are big numbers. So it's nothing, 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 a big number. There it is. That's actually the 30 hertz signal that I'm going to be looking at there. Okay. Right, so I know that I think by peeking at it, I think I got the right answer already. 355 plus minus 355J is a big number, and so I don't know what to do with that yet exactly. So I'm just going to hold off for now. We're going to have to learn how to normalize the data that's coming out of the FFT algorithm to make it look right, to make it the right numbers. Okay. The other thing we need to do is I don't care about the angle so much. I really want to know what the magnitude is because I'm going to match that 3, 1, and 2. I know that the coefficients in front of those three cosine waves are 3, 1, and 2, and so I want to see that. Okay, so the way to do that is to get the magnitude of capital X, and that's the ABS function, absolute value. So by taking the absolute value of a complex number, you get the magnitude of that number, right? So I'm calling that X underscore mag, and that's equal to the absolute value of capital X. I can just plot that, right? I'm just going to plot that variable alone. No x-axis, just the y-axis, right? So it's just the index of the value is just going to be shown up. And when you see that, you can see there's three numbers. They're big, though. The y-axis is huge, but you see three numbers, and then you see at the other end, on the right side of the graph, you see three more numbers. This is what we all know and we're all predicting is wraparound, right? So around the middle frequency there, the 500th point of these 1,000 points in this file, the data is going to be wrapped around that center frequency, and so you're going to see that. So we do. That's comforting. That's good. But what we need to do is we need to make the x-axis right, and we need to make the y-axis right. So that's the next step. The first thing I'm going to do is I'm going to make the frequency axis, right? So the way the frequency axis works is it starts at 0, the average value of the signal. So it starts at 0, and then it increments by the fundamental frequency f0, right? f0, 2 f0, 3 f0, and so on. f0 is just equal to 1 over the whole period, which is n times delta t. So I calculate what f0 is, and I regenerate the frequency axis. You see it right there, 0 colon f0 to n minus 1 times f0. Right, to go right up to 999 hertz or whatever. All right, so so that's the x-axis. So I've got that worked out, right? And when you plot it, you can see, and we can't quite see yet, But you can see that the 20, 30, and 40 hertz are probably going to line up right. That part looks okay. I'm starting to have confidence in that. The y-axis. What do we do with the y-axis? Well, what you have to do is you have to normalize the data, the absolute FFT data, by n over 2. You have to divide by n over 2. So if you divide it all by n over 2, 500, right, then plot it. And the other thing we want to do is we want to make the axis right. So I just want the first, 60 or so points there. So I go up to 60 hertz. And then I want to plot the data in red circles because I want to see if it's just 1 point each. And lo and behold, you take a look at that graph, and there it is: 3 at 20 hertz, 1 at 30 hertz, and 2 at 40 hertz. The magnitude of the signal at each of those three frequencies. The frequencies match up, the magnitudes match up. It works. This is how you do all FFTs. You just have to get the right axes. You have to get the right frequency axis. Delta T, and you have to know all the different equations for sampling frequency, delta T, and F0, and those kinds of things. And then, so to generate the frequency axis, and then you just have to normalize the y-axis, the absolute value, by n over 2. That's the trick.